It's the first of our chemistry lectures. There will only be two, this one and the one that we will do next week, and then your exam. The notes that I handed out today include both lectures, so if you picked up a set of these notes, make sure to bring them back with you next week because the second chemistry lecture is also included in that packet. All right, so back to the hierarchy. If you'll remember when we looked at that hierarchy in the first lecture, I said we'd revisit it in more detail. And here it is in more detail. So the next three slides are a much more detailed hierarchy that you'll need to become familiar with. So down on the chemical level, the smallest unit is an atom. Okay? We're talking periodic table of elements. Carbon, hydrogen, oxygen, nitrogen. These are atoms. Atoms come together to form molecules. Okay, those are combinations of atoms that are bonded to one another. Molecules will come together to make a macromolecule. What is macro? Large. If micro is small, macro is large. Macromolecules are large molecules. Macromolecules will arrange themselves into what are called organelles. These are individually functioning units of the cell, like the nucleus, the mitochondria, the Golgi. These are all organelles of the cell. When we take all the organelles together, that's when we get a cell. Okay, so on this whole slide, we've only gotten ourselves to cell. We go to the next slide. Cells organize themselves into tissues, tissues into organs, organs into organ systems, and this is supposed to be showing you the nervous system of this bird. I know it's hard to tell. And what color should they have drawn that in? Yellow. Should have been drawn in yellow. And when we take all the organ systems together, we get an organism. Now, we're very familiar with this slide. It's almost identical to the first hierarchy we're looking at. But what we didn't look at is how this hierarchy goes even to a larger scale. When we take many organisms, many of the same organisms, and put them together, we get a population. When we take populations that exist side by side, we're going to get a species. When we take several species living in the same area, we get a community. And when we take all the communities that depend on one another, we get an ecosystem. Okay? The same way that you depend on tissues and cells and organs is the exact same way an ecosystem depends on the soil and the water and the sun. Every one of the things we've talked about in this hierarchy is completely interdependent on the other levels. You cannot remove one level and have the whole thing still stand. It would all come crashing down. So everything is dependent on the level below. So for today, we're down here on the atomic level. That's where we are going to talk about chemistry. We will get as far as macromolecules in the two chemistry lectures. So for the next two lectures, we're only talking about these first three levels. Today, again, we're on the very bottom with atoms. So the definition of an atom is an extremely small particle that's made up of matter. Great, but what is matter? Matter is any substance in the entire universe that has mass and occupies space. It is very broad, it is very general, it is very vague, and that is on purpose. Okay? It is something to categorize substance in the universe. It has mass and it occupies space. How do we know what atoms look like? Okay? The truth is, we don't. We have no idea what atoms look like. We can only guess what atoms look like based on their behavior. And a long time ago, a guy named Niels Bohr came up with a model of what an atom would look like that explains almost every behavior we see by atoms. Okay, so Niels Bohr proposes that every atom possesses an orbiting cloud of tiny subatomic particles. What's a subatomic particle? What's going to be its size relationship? Is it going to be larger than an atomic particle or smaller? Subatomic particles are smaller than atoms, than atomic particles. These tiny subatomic particles are what we call electrons. Okay? So we think that electrons are orbiting around the outside of an atom and that they're very, very small. At the core of all the subatomic particles, the electrons, is a small, dense nucleus of other kinds of subatomic particles, protons and neutrons. So Niels Bohr supposes that any one atom is not just a little molecule. Carbon is not just a little circle, and then nitrogen is another one. He supposes that every atom that we think of is actually made up of several smaller particles, protons, neutrons, and electrons. That's what this picture is. These are both Bohr models. Okay? This one is showing you the cloud, and this one is showing you what would be, for all intents and purposes, a still photograph. So if this electron was allowed to move, it would look like this. It would be a blur around the outside. If we could hold it still, we would see it in one spot orbiting around the outside of the nucleus. Here's a different atom. We see the nucleus of protons and neutrons in the middle. Around the outside would be a blur of electrons. Okay. Each subatomic particle is assigned its own charge. Protons carry a positive charge. That's always easy for me to remember because proton starts with P and positive starts with P. Protons are positive. Neutrons are neutral. Don't think that neutrons are negative. Okay? Take the first couple letters, N-E-U-T. Okay? Neutron, neutral. So that means they do not carry a charge. Electrons, the ones that orbit around the outside, carry a negative charge. Okay? Typically, an atom has one electron for every proton. So if we see a proton in the nucleus, we are likely to see an electron in the cloud orbiting the outside. If we see two protons, we see two electrons. 3 protons, 3 electrons. So we can say then that we can now start to assign characteristics to these subatomic particles. The number of protons of any atom is now going to be equal to its atomic number. Okay? The atomic number will indirectly determine the chemical character of the atom. Now, why does it indirectly determine that? When atoms interact with each other, they do it through their electrons. Okay? They can share electrons, they can steal electrons, they can give electrons. So when we see hydrogen and oxygen wanting to get together, they do it through their electrons. Okay? And now we know that the number of electrons is typically equal to the number of protons. So if we know the number of protons, then we know the number of... This is why the atomic number indirectly tells us how that atom will behave. If I know the number of protons, then I know the number of electrons. And when you get heavily into chemistry, based on the number of electrons, you know how that atom's going to want to interact with other atoms. So that's why it's indirect, because we're using one number to extrapolate another number. Orbiting electrons, again, are what are available for chemical activity, which is bonding. You either share electrons, you give up electrons, or you take electrons. Those are the only 3 things that atoms can do to each other. So the number of protons equals the atomic number. Stick that in your brain, because I will be asking you the atomic number of atoms again and again and again. You have to remember it's the number of protons. Okay? For example, here's hydrogen. Hydrogen has 1 proton, and we already know that for every proton we usually have 1 electron. So 1 proton, 1 electron. What is the atomic number of hydrogen? 1. Here's oxygen. 8 protons and 8 neutrons. We know that the number of protons should be equal to the number of electrons. We see 8 and 8. What's the atomic number of oxygen? Which 2 particles exist at the core of that atom? Protons and neutrons. This mass right here in the middle represents 8 protons and 8 neutrons, and then the 8 electrons float around the outside. If an atom has the same number of protons and neutrons, will it carry a charge? Why? Because the positive cancels the negative out. If you have 8 positive charges and 8 negative charges, they cancel each other out. Here's just a quick picture of the periodic table of elements. One of the ways that the periodic table of elements is organized is by atomic number. Starting at the left, going to the right. You see the number 1, 2, we come back, 3, 4, 5, 6, 7, 8, 9, 10. That is the atomic number or the number of protons. Good. Here's another picture of an individual element. The chemical symbol is the letter or letters in the middle, full name underneath, and then which one of these is the atomic number, right or left? It's the 8. 8 was the atomic number of oxygen. Okay. Atomic mass is another characteristic of atoms. Okay? They're very, very small, but they do have a mass. What is mass? Mass is the amount of a substance, which is different than the weight. Weight is the force that gravity exerts on a substance. So, Moon versus Earth. If my mass is 56 kilograms on Earth, what is my mass on the Moon? 56 kilograms. It's exactly the same. But what will my weight be on the Moon? Will it be more or less? Less, because there's less gravity on the Moon. So the number that, or the way that you're used to dealing with substances is almost exclusively in weight. Okay? We're always used to figuring out the force that gravity exerts on something, but you have to realize there's a difference between weight and mass. We can take away the force that gravity exerts, and we can find out just exactly what amount of a substance exists. Atomic mass, okay, on the atomic level, is equal to the sum of protons plus neutrons. So there's another definition you need to stick in your brain, because I'm going to ask you the atomic number, I'm going to ask you the atomic mass of several atoms on your exam. So all you have to do is find the number of protons, the number of neutrons, add those numbers together, and that will give you the atomic mass. Okay? Atomic mass is measured in daltons, which is not something we usually deal with in an everyday situation. We say that 1 proton equals approximately 1 dalton, and if you haven't seen that squiggly line before, it's called a tilde. In science, that means approximately. Okay? And 1 neutron weighs approximately 1 dalton. One weighs a little bit more, the other one weighs a little bit less, so for the simplification in this class, we're going to say they're equal to 1. An electron weighs almost 1/2000th of a dalton. That's too small even for scientists to deal with. Okay? Scientists are very meticulous and they like to count everything. Electrons are too small. We don't even count them towards atomic mass. To give you an idea what a dalton is, 1 gram, which is about the weight of a very small paper clip, is equal to 602 million billion daltons. Okay? Just to give you some kind of frame of reference for what a dalton is. This number, 602 million billion, if you stay in chemistry, if you stay in physics, you're going to run into it again and again and again. It's a conversion factor called Avogadro's number. 6.02 times 10 to the 23rd. This is the exponential way that this number is written, and million billion is longhand. Okay, back to hydrogen and oxygen. What is the atomic number of hydrogen? 1. What is the atomic mass of hydrogen? What's the definition of atomic mass? Protons plus neutrons. How many protons are in hydrogen? How many neutrons are in hydrogen? 0. 1 plus 0 is 1. Okay, so atomic number is 1, atomic mass is 1. What's the atomic number of oxygen? What's the atomic mass? 16. Okay, 8 protons gives us that atomic number. 8 protons plus 8 neutrons gives us the atomic mass. Good. So again, the mass of any element given in the periodic table of elements is always below the chemical symbol. You'll usually see it indicated with a decimal point as well. That also gives away mass. Atomic number is always above the chemical symbol. Atomic mass always below. Isotopes. Okay? Just when we thought we had some hard and fast rules, we're going to change them. Isotopes have the same atomic number, but a different atomic mass. So just by that definition, you should be able to figure out what they have different. If I have the same atomic number, then I have the same number of protons. But if we all have a different atomic mass, that means we must have different numbers of neutrons. Isotopes have the same number of protons, but a differing number of neutrons. If we look at carbon, carbon comes in a few different forms. Carbon-12 being the most common. That's what you're made out of. That's your favorite energy source is carbon-12. It has 6 protons, 6 neutrons, and 6 electrons. There are other forms of carbon. Carbon-13, which has 6 protons and 7 neutrons. Carbon-14, 6 protons and 8 neutrons. These are called isotopes. They all get the same name, carbon, 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 but then we specify that they are isotopes by adding carbon-12, carbon-13, carbon-14. So again, same atomic number, same number of protons, but a differing atomic mass, which gives them a different number of neutrons. Why is this important? Isotopes tend to be unstable. Okay? Carbon-12 is very stable. That's why it's the most common type. Carbon-13, carbon-14 are not stable. They're not happy having more neutrons. So the nucleus, where the protons and neutrons exist, tends to break up into elements with lower atomic numbers. Sometimes it can get rid of neutrons and go into carbon-13 or carbon-12. Sometimes it'll break into totally different elements. When this happens, a humongous amount of energy is released, and it's called radioactive decay. When the nucleus of an atom breaks up and energy is released, that's called radioactive decay. Carbon-14 is then considered a radioactive isotope. What do we use radioactive energy for? X-rays. What is the field of imaging technology called? Radiology is one. There's an even bigger name for that field. You're in the practice of blank medicine. Nuclear medicine. Imaging falls under the category of nuclear medicine, which gets its name because you are manipulating the nucleus of atoms, which gives you radioactive energy, which is why it's called radiology. Okay? All of these things actually just tie right back into chemistry. So nuclear medicine, which includes radiology, has to deal with isotopes. Okay? Again, radioactivity being released can be harnessed and used for imaging. You can send it through the body, and it bounces back in a pattern that gives us an image. That's an X-ray. Exposure to radioactivity always has to be monitored. If you go into radiology, you'll become very familiar with lead. Lead can stop a good deal of radioactive energy, and most people who work in radiology wear a badge that measures their exposure to radioactive energy, and then if it gets too high, then you have to stop working with it. So always be aware if you're going into that field, or you go into any field, even dentistry, they take X-rays, that you always have to monitor your exposure to radioactive energy. Okay, charge and chemistry. Electrons can cause different atoms to carry a charge. For a review, we remember that protons are positive, neutrons are neutral, and electrons are negative. And we said typically, for every positive charged proton, you have a negatively charged electron. Typically, not always. That doesn't say always we have that, but just typically. So when atoms have the same number of protons and neutrons, or protons and electrons, they're neutral. That's no charge. Okay? It's a neutral atom. But when the number of electrons does not equal the number of protons, that's an ion. We didn't say which way the balance was. We didn't say which had more and which had less. We didn't say there's more electrons or there's more protons. We didn't specify. We just said they're not equal. So that's an ion. Okay? When you have more protons than electrons, you have a positive net charge because protons are positive. If you have 7 protons and 6 electrons, you have 1 extra positive charge. That makes a cation. Okay? A cation specifies that you have a positively charged molecule, or atom, sorry. When you have more electrons than protons, you have a negative charge. You're carrying more negative charge than positive. That's an anion. Okay, so the word ion just says charge, doesn't say which one. Cation says positive charge, anion says negative charge. Okay, I am going to stop and quiz you guys. Okay. Marker's horrible. Start bringing them with me. That one's not much better. Okay, so let me just draw a table because this is the exact same thing that's going to show up on your exam. Let's compare 3 atoms. We'll say atom A, atom B, and atom C. Oh, that's not better. All right. I'm going to have to start bringing markers with me. Okay, and we'll say that, oh, now that one's dead. Say protons, neutrons, and electrons. Let's see. Okay, here's my chart, atom A, B, and C. You can see the number of protons for each element, the number of neutrons for each element, and the number of electrons for each element. Okay, now I get to ask questions. Does atom A have an isotope? How many people say no? How many people say yes? Which atom would you think is its isotope? B or C are your only choices. You think both are isotopes of A, or C is an isotope. So what's the definition of an isotope? Same atomic number, but a different atomic mass. So they have to have the same number of protons, but a different number of neutrons. Which atom has the same number of protons? A and C have the same number of protons. They also have the same number of neutrons. So are they isotopes of each other? No, there are no isotopes on this chart. Okay? There are no 2 elements that have the same number of protons but a different number of neutrons. Okay? Second question. What's the atomic mass of atom B? 10. 5 protons plus 5 neutrons equals the atomic mass. What is the atomic number of atom C? 4. Number of protons. Do any of the elements on this table carry a charge? So in order to determine charge, we have to compare the number of protons to the number of neutrons. 4 and 4. Any charge here? 5 and 4. Which way? What's the charge? Positive charge. 4 and 5. Good. Okay. Does everyone see how we got all the questions and answers? Because that's exactly, well, not exactly, but that's very similar to what's going to show up on your test. I will give you several elements. I will ask you, are there isotopes? What's the atomic number? What's the atomic mass? Is anyone carrying a charge? If they are, what is their charge, positive or negative? Okay? So make sure that you know your definitions of atomic number, atomic mass, of charge, of isotopes, and that you can identify them. Okay? All right, energy. All atoms possess the ability to have energy because they can all do work. Work and energy are very interchangeable, very related words. Atomic energy can be likened to a rubber band. If I were holding a rubber band, and I usually remember to bring one with me for this lecture, and I've forgotten. If I'm holding a rubber band and it's loose, there's no energy in it. If I stretch it out, all that I have done is transfer energy from my skeletal muscles into that rubber band. If you want proof that there is energy in that band, hold one end against your leg and let the other end go. Okay? What stings your leg is the transfer of all that energy onto your skin. That's all it is. You transfer energy out of your muscles into the rubber band. Again, you want proof it's there, flick your friend with it, flick your leg with it. You are feeling the transfer, the release of that energy. So if you want to move energy into the system, you take an electron and you move it away from the nucleus. You move it away from the core. That stores energy for that atom. Okay? The rubber band in this situation one end has to be anchored to the nucleus, the other end to the electron. If you want to put energy in, we move the electron away. If you want to release energy, you bring that electron back towards the nucleus. So it's just the movement of the electron that can store energy or release energy. And here's the picture. Don't worry about energy levels. Just look at the nucleus of the atom and the movement of electrons. Again, if we want to absorb energy, if we want to put energy into the system, we must move that electron away from the nucleus. If we want to release energy, we move that electron back towards the nucleus. Energy has many forms. Okay? Yes, you can do work. Another type of energy is light. Fluorescent lights, okay? The reason it's casting light is because electrons are constantly moving down towards the nucleus. What do you think happens when that light doesn't work anymore? If it's giving off light because electrons can move towards the nucleus, when it's not giving off any more light, what must have happened? All the atoms that were in there move. You can only move it once. You can't put it back out. You can only move it down once. So it ran out of atoms that can move their electrons. Then a fluorescent light doesn't work anymore. Okay? All sorts of energy. It can come off as light, heat, work. These are all types of energy. Another good example of energy to think about is photosynthesis. Okay? Plants get their energy from sunlight. But when the sunlight goes down and it's dark, the plants don't die. The reason is because when sunlight hits a plant, all it helps that plant to do is, on a very atomic level, a simplified atomic level, the sunlight takes the electrons and moves them out. And it allows that plant to store energy. Then the sun goes down, and the way that that plant stays alive is by moving those electrons back down and releasing that energy and using it to do processes through the night. Sun comes out the next day, electrons store that energy by moving away. Sun goes down, electrons move back down towards the nucleus. Okay? That's incredibly oversimplified, but in a nutshell, on an atomic level, that's what's happening. And that's what happens in your body every day. Any system that has energy that does work on an atomic level, that's what's happening. Oxidation and reduction is another behavior of atoms, and it has to do with the exchange of electrons. Electrons can be transferred from one atom to another. Remember, we said you can take electrons, you can give electrons, or you can share electrons. Those are your only three options. If you are losing an electron, that's oxidation. Okay? If you gain an electron, that's reduction. So this atom that had an electron lost the electron to this one. So this one has undergone oxidation, the one on the left. The one on the right has undergone reduction. Okay? The energy, which is the distance that this electron was from each nucleus, does not change. Its distance from nucleus 1 is the same as its distance from nucleus 2. Everyday examples of oxidation and reduction: rust on your car. Okay? If oxygen can get to the metal of your car, it steals electrons from it. Okay? And when it steals enough electrons, the metal begins to degrade and it looks like rust. When you go into the grocery store and you go to the meat counter and you want your meat to look really bright red, but some of it looks kind of brown, that's just oxidation. Okay? There's nothing wrong with that meat, except that the oxygen has been stealing electrons from that meat, and it turns the meat from red to brown. There's nothing wrong with that meat. So when it's on sale, you should buy it. Okay? Again, the periodic table of elements, where all of our atoms are listed, is organized several different ways. We saw it organized by atomic number, or the number of protons, the number of protons. That's one way we organize the periodic table of elements. For most of the atoms that are important to life, okay, carbon, oxygen, nitrogen, hydrogen, these are atoms that are important to your life. The outer energy level can contain no more than 8 electrons. And this is leading to another way that the periodic table is organized. 8 is the magic number for atoms that are important to you. Elements that have all 8 are satisfied and will not react with any other atom. It doesn't matter what atom you put in their presence. They won't take from it, they won't give to it, they won't share with it. They are called inert because they will not react with any other atom. We can usually find them in gaseous form: helium, neon, argon, krypton, xenon, radon. Okay? Those are inert gases, meaning that they have 8 electrons. They don't want any more, they don't want to give anybody any more, they don't want to share any. Okay? And they are inert. Helium we're all familiar with. Neon and argon, where do you guys see those mostly mentioned? Neon lights. Neon lights are usually filled with neon or argon gas. These other ones you don't really see that much. Radon gas is not good. But these are ones that have all 8 electrons. If we take one away, elements with 7 electrons are highly reactive because they are so close to having 8 electrons that they are literally freaking out. They will steal that 8th electron from anybody else except for, of course, the inert gases who they can't get it from. They will take that 8th electron from wherever they can get it. Fluorine, chlorine, bromine. Where do you guys see these used the most? Swimming pools. What about fluorine or fluoride? Toothpaste. The reason that these particular elements are so good at controlling the tooth decay in your mouth or the microbial growth in your swimming pool or hot tub is because on an atomic level they are running in and stealing electrons and slowly destroying whatever it is that you find harmful. Okay? And the reason that they have that power is because they have 7 electrons and they want that 8th electron from wherever they can take it. Here's our periodic table of elements again. Here are your inert gases. Notice they are all in a column on the right-hand side. Again, told you this was leading to another level of organization. Not only are we organized by atomic number, but also organized into columns. Here are ones with 7, fluorine, chlorine, bromine. The ones in blue are the ones important to your life. Okay? Your body is mostly made out of nitrogen, oxygen, carbon, and hydrogen. That's 96.3% of your body. Out of the 103, which this is an old one, I think there are over 120 elements now. Out of 120 elements, you're really mostly just made up of 4. Okay? Nitrogen, oxygen, carbon, and hydrogen. That's the majority of the weight of your body. Okay? And here they are. You'll see that they're all pretty close to each other on the periodic table. There's hydrogen, carbon, nitrogen, oxygen. 1, 6, 7, and 8. Okay? You're not made up of anything down here. All your important elements are in blue, and the majority of you are just those 4: hydrogen, carbon, nitrogen, oxygen. All right. The last thing we're going to talk about before we stop today are chemical bonds. Okay? We said that when atoms interact with each other, they do it through their electrons. Okay? When they interact through their electrons, that's called a chemical bond. Okay? They're held together by energy and a stable association. That means something has changed about their electrons. And when we have more than one atom together, it's called a molecule. Okay? Atoms of more than one element joined together are called compounds. So a molecule just says to us there's 2 atoms are together. We didn't say if they're the same or if they're different. If I tell you I have a chemical compound, that automatically means by definition they are not the same element. Like water, hydrogen and oxygen, that's a compound. But if I stick a bunch of oxygens together, that's not a compound, that's just a molecule. Okay? Atoms in a molecule are always joined by chemical bonds. There are 2 types of chemical bonds, ionic and covalent. We're going to talk about ionic today, and we'll talk about covalent next week. Ionic bonds form when atoms with opposite charges attract each other. A positively charged atom attracts a negatively charged atom. Covalent bonds happen when atoms share, because remember we said they could take, give, or share electrons, when they share pairs of electrons. And the real key word there is pairs. They're sharing 2 electrons, or 4 electrons, or 6 electrons. Again, we want to remember that charge is due to changes in electrons. If you have more electrons than protons, you're going to carry a negative charge. If you have more protons than electrons, you're going to carry a positive charge. All right, so here's an example of an everyday ionic bond. What is sodium chloride? Salt, common table salt. Put it on your food every day. It's sodium chloride. In their native situations, sodium and chloride do not carry charges. But if we look at their outermost energy shell, sodium only has 1 electron, and in the outermost energy shell of chlorine, we see 7. And we've already said that chlorine is highly reactive. So it seems like a match made in heaven. Sodium only has 1 in its outer electron shell, and if it gets rid of it, then it gets to drop down to the shell below it, and that one's already got 8 in it. So if it could just get rid of 1, and chlorine could just have 1 electron, they would both get to have 8 electrons, and everyone would be happy. And that's exactly what happens. Sodium donates 1 electron to chlorine, making it chloride. Now they're very, very happy because they have 8 electrons in their outer energy shell, but sodium has lost an electron. So now it has more protons than electrons, so its charge would be positive. And chloride has gained an electron, so now it has more electrons than protons, and its charge would be negative. So now they're attracted to each other. Okay? So what brought this about was that 8 is the magic number rule. Okay? That kind of overrules everything else. They each wanted to have 8, so sodium gave up an electron, chlorine gained an electron, making it chloride. And now they each have 8, but now they're going to be attracted to each other because of opposite charges. So sodium chloride is what we call an ionic compound. There are no discrete sodium chloride molecules. What happens is that you cannot forget that electrons are constantly in motion. Excuse me. So this 1 chlorine in the middle is actually sharing its electrons with all the surrounding sodiums. because remember the electrons are moving. And this sodium is sharing electrons with all the surrounding chlorines. It leads to an aggregation, and that's why you see a salt crystal. Okay? All right, questions? All right. We will finish second chemical lecture next week. Fetal pig dissection today, so don't forget your gloves, something to cover with. And we're having our quiz, our lab quiz, first thing in lab at 11 o'clock.